Okay, so back to sets. So we want a set to be well-defined. That can be questionable. Set contains elements. Set can be empty, means it can have nothing in it. Sometimes you'll see the empty set written with that symbol there in the book. It's not a zero. The line goes through and extends a bit. So a set can be empty. When we list the elements of a set, we don't repeat them. We'll get into that when we talk about unions in just a moment. Other thing about sets is set will have the attributes of quantity. So the idea of counting, which is one of the first things we learn to do mathematically, comes from the idea of sets. Right? The idea of 5 comes from the ideas of sets. So when we ask the question, how many, that's where numbers start to come from. And mostly that stuff was in section 2. In section 3, we go over some operations of sets, and we didn't get to do much with this yet. And there's essentially 3 operations we're going to be concerned with sets. Getting the complement of a set. So for example, if my universe was counting numbers that are less than 10, and I let set A be, let's say, the even numbers in there, I would denote the complement of A with a bar over it. It's one way to do it. Sometimes you'll see A with a C, little c next to it. Depends on what book we're looking at. And that means everything that's not in A, in whatever your universe is. Now, sometimes we can name the complement of a set, like what's the opposite of even? Ah, that works. But what if I was talking about positive numbers? What's the opposite of positive? No. What is it? It's not positive. Yeah, so sometimes we do have a special name for the complement of something, and sometimes we don't. Sometimes it's more complicated than that. So we do want to be careful about that. So evens in this set, more specifically, I could say were the numbers, let's see, counting numbers 2, 4, 6, and 8 would be the things in set A. In the set not A would be everything else in the universe. So 1, 3, 5, 7, 9, and I think I've got everything. So complement is one operation we can do to a set. It changes it somehow. Another popular operation is the idea of union. We talked about this back in the logic section. Union, we use the word or often. Howdy. And with an or, we put them together. And the usual symbol for union is a U without a little line on the end. Sometimes it's called a cup. So if I take set A and I put it together with the complement of A, that should give me everything in my universe in this case. which is universe is a pretty capital U usually. So we don't want to distinguish whatever is our universal set with the idea of a union, two different things. We have a universe and a union. So notice when I make my U for union, I don't put any side line on it. So be careful that you don't confuse those in your notes. What was my universe here? My universe was counting numbers less than 10. We can also work with Venn diagrams when we're playing with sets. We did a little of this in the logic section. And so here I'm playing with set A and set not A, which is A with the bar over it. So let's see, A was the set of even numbers. So that would be, for example, 2, 4, 6, and 8. And not A had everything else in this universe, which was 1, 3, 5, 7, and 9. And a union comes when you put two sets together, and that's that figure 8 shape we played with a couple weeks ago. Does anybody remember what we called this crescent shape in the middle? What is it? Yeah, it's the intersection. And intersection is another operation we can do with sets. It's a way to combine sets. So we're going to take a look at intersection next, then we'll play with a bunch of different examples. So another thing we can do with sets is look at their intersection. So let's stick with the same universe. And oftentimes when we're playing with sets, we give more formal definitions. And so usually for set notation, you'll see a curly bracket indicating I'm about to describe a set. Often we'll do something like give a variable for the set, maybe an n or an x or something else. Then we put a bar. The bar means such that. And then we list anything that describes how to determine what's in this set and what's not. So, so this says the universe is the set of all n such that n is an element of the counting numbers. An element is usually a funky little e like that. Comma, and then any other conditions. The other condition I implied was that the n's were less than 10, and then close your parentheses. So that's just called set notation. You might have seen it in algebra class before. Anyone remember seeing something like this in an algebra class? Some people not. Kind of depends who you had for algebra, whether they showed you set notation. It's in most algebra books if you actually read the book. But most people don't read algebra books. So that was my universe. Set A, if I define it formally, was the set of n. And again, I'm in my universe. I don't need to restate that. And here, I just wanted n to be even. N is even. There are other ways I could describe being even. I'm just going to say that. And let's introduce a new set B. Set of all n's such that n is prime. So there's two ways to talk about a set. One is to describe the set with conditions, and the other is to just list everything that's in the set. Okay. So what's in A here? 2, 4, 6, and 8, yeah. 2, 4, 6, and 8. And what lives in set B? Which of our numbers in our universe are prime? One's not prime. to be prime, you have to have exactly two different factors. And one factors is 1 times 1, so it doesn't count. So it would be the first prime then. Two. And then 3 and 5, 7. Okay, but we're staying in our universe, right? So 11 would be, but in this universe, we're done. Can't go up past 10. So that's the prime numbers here. And so now what I want to take a look at is a new set by taking set A and intersecting, so an upside down U, or a cap, it's usually called. What happens if I intersect A and B? So with intersection, we use the cap symbol, and in words, it's an and. So I want everything that is even and prime. 2 is the only number that's even and prime. So that would be the intersection of these two sets. So what I'd like you to do next is draw a Venn diagram of this scenario. Like I drew a Venn diagram of A and not A. So draw me a Venn diagram. Put something down, and I'll draw mine, and hopefully we agree. So Sheila said earlier that that crescent in the middle, that represents our intersection, so that's where 2 should go. And then, for example, 4 is even, but it's not prime, so it goes definitely right there. 1, it's not even, right? And it's not prime, so it goes out here. 3 is prime, but not even, so it goes in that crescent. 4, 5, prime, right? Oops, whoa, that's a weird 5. Oh well, we'll go with it. 6, even, not prime. 7, prime, not even. 8, even, not prime. 9, it's, yeah, somewhere out here, could be by the 1, anywhere outside of those two circles. And we were trying to illustrate the scenario I started, which was, okay, where do the things in A go? Where do the things in B go? Where does A union B go? All right. Or sorry, intersection, A intersect. So there's our intersection right here. Let's highlight that sucker. Oops, I want a highlighter. So that right there is A intersect B. What if I wanted to figure out A union B? So what numbers are in set A or set B? So what n such that n is an element of A or n is an element of B. So that's what union means. Let's see, how many things were in set A? 1, 2, 3, 4. How many were in B? How many are going to be in the union? At most 8. Why am I saying at most 8? Yeah, because they both count the 2, right? So if there's an intersection, then when I put them together, I don't want to double count the 2, right? So whenever you take the union of two sets, you can have at most however many were in the first set plus however many in the second set. But we just can't say 4 plus 4, there's 8 in there, because that would double count 2, right? So that's a problem. And when we list sets, we don't double count the elements in the set. So we can just kind of go through and list the elements. Let's see. Is 1 in A? Is it in B? So it's not in the union. Is 2 in A? Yes. I don't care whether it's in B. It could be. Who cares? It's in A. So I can say 2 is in there. How about 3? Is 3 in A? But it is in B, so that gets the OR. So 3 is in there. 4 is in A. We're good. 5 is in B. We're good. 6 is in A. We're good. So as long as it's one in one or the other, I got it covered. 7 is in B. 8, A. 9, neither. And I ran out of things. So how many things did I get? 1, 2, 3, 4, 5, 6, 7 of them. Okay. Unions just put them together. This would be inappropriate to list all the elements of A to, whoa, it's supposed to be a comma, 4, 6, 8, and then list all the elements of B, 2, 3, 5, 7, and say, that's the union. Again, what's wrong with what I just wrote? I wrote 2 twice. 2 is the same thing. It doesn't make any sense to write it twice. So that would be an inappropriate way. Okay, unless you went back in and erased the 2, that would be okay. Don't double count it. So or is one or the other or both, or is this figure 8 if I have 2 sets to work with. Or means to put together. Yeah. So what things do I have to put together? I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. But I got to put them together such that they meet this description or they meet that description. Now, does anybody remember about the word or in math compared to the or in regular language we talked about a couple of weeks ago? My example on that was with my kids. What was the example? Almost. That was just the like the implication, the promise thing. Ice cream or cake? Yeah, that was the example. So if I go home tonight and they say we want dessert, and I say you can have ice cream or cake, what does that mean to them? One or the other. They can't have both though, right? So that's called an exclusive use of the word or. In math, or is an inclusive, meaning you could meet one condition, you could meet the other condition, but you could meet both conditions. That's okay. So or means put them together. Got to meet one condition or the other condition or both. And means they have to meet both conditions simultaneously, right? So which number here or numbers are both even and prime? Right, and that's that yellow intersection in the middle. The yellow intersection in the middle is my and. So this symbol right here means and, whereas this symbol over here means or. So or means the figure 8, and is that little crescent in the middle. Where do they overlap? What do they have in common? So or, throw them together. And what's common? Okay. All right, so now we're going to get a little bit more exciting. So they have to meet both descriptions. Yeah, 2 is both even and it's odd. So next we're going to start getting a little fancier. And look at what's possible when we take a set of 3 things and throw them together. So if you throw 3 sets together, they could interact in this way. Now, any one of these regions could be empty, but they don't have to be. And so I'm going to pick a cute problem from the book to use to analyze this. Wrong class. That can all go away. Where is the right class? That's not it. That's it. Okay, and I forgot my book, so we'll get the digital book. Actually, I know what I'll do. We will grab one of those practice tests. Let's see, does this one have any fun problems on it? Oh yeah, this is a fun one. Let's blow this up. Actually, I'll steal it. And I will get you guys copies of this. Oh, I didn't print enough copies of this one. All right, everybody that wanted one of those, grab one, and I will print some more of the other one. Print. Do you want a copy of the practice test, or do you have one? All right, let's see. How about this one? All right, let's take a look at this one instead, because you guys all have a copy of this one. So if you look in your activity book, you should have a set of punch outs figures like this right here. And they are called attribute pieces. So if you don't have that, then you're just going to have to look at my sheet or your neighbor's to figure this part out. Let's see, I've got another one somewhere. Documents, Math to 11. Okay, so here are those shapes here. Can I blow that up a little bit? It's kind of too big. All right, so we're going to play around with these guys. So this is my universe right here. That's too big. I'll have to blow it. All right. So what do we have in this universe? Well, we have shapes, right? Okay. The shapes are either square, triangle. What can we call that next one here? A rhombus would be the perfect name for it. Some people call it a diamond, which isn't technically a mathematical shape, but that's okay. When we have a circle. And each of those shapes could either be big or small, and they could either be blue, red, yellow, or green. Okay, so attribute means a quality of something. So these shapes have three different qualities. They have shape, they have size, and they have color. And so we can play around with them that way. So what we're going to try and do is from this universe, we'll come back and do that math one in a little bit. New page. We are going to try and solve this problem here. Blow it up. How do I make that go away? Go away. All right, so set A is going to be not square. B is going to be small. And C is going to be red. And we are going to try and put those into this figure right here. So if you have them in front of you, great. Otherwise, I will put them up here on the screen too. All right, so I'll label this a little bit more. Pen, got it. Okay, so set A, remember, those are my not squares. The B's are my smalls. And the C's are my reds. Now, if I were working with younger children instead of adults, and even with some adults, I would have these shapes all cut out, and we would have circles of string or yarn on our desk in this configuration, and we would throw the pieces in the right spot, okay? For now, we're gonna try and reason through this and count. So for example, how many small shapes are there in this grid? So let's see, we have 4 by 4, so there's 16. So in this red circle, there are 16 pieces. Now I don't yet know how many go here, 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 and here, but I know in there somehow 16 pieces have to go, okay? And then there's some red pieces. How many red pieces are there? There are 4 and 4, so there's 8 altogether. Some of those 8 live here, some might live here, some live there, some live there. So I have to try and figure out where they go. If we pick on, say, this region right in the very middle there, how would you describe a shape that sits right there in the middle? Yeah, it has to meet all 3 characteristics. It would be the intersection, so it would have to be not square and small and red. Are there any shapes that fit the description, not square and red and small? You think there's 3 of them, so let's double check. So in this region over here, I have those shapes, right? And I want, so those are my smalls. In the smalls, I want the reds, so I narrow it down to that group. And then of the reds, I want the not squares, which are those 3 right there. So it looks like we found there's 3 that sit in that intersection. I'm going to clean up this mess a little bit. And I'm just going to make a note that there are, oops, wrong tool, that there are 3 shapes in the intersection. All right, so let's see. If I zoom out a little bit and I go for this crescent shape right there, what describes things in that crescent? They're small and they're red. How many shapes are small and red? 4, but we've already accounted for 3 of them, right? Okay, so how would you describe then the pieces in just this region right there? That one piece. Yeah, it would be the not square, which makes it square. So it would be the small red square is that one piece right there. So we're going to try and reason how many pieces are in each of these corrals. So we think there's 1 right, oops, wrong thing again. There's 1 right there. All right, let's see. How about this other lower crescent over here? How would you describe shapes in that crescent? Yeah, they're definitely red and they're not squares. Okay. Yeah, it doesn't say anything about size there. So they could be big, they could be small. So if I'm thinking about red not squares, well, there's 1, 2, 3, 4, 5, 6 of them. And I've already accounted for 3, haven't I? So in that other cut crescent, there should be 3, right? So I think that there, oops, I keep doing that. It's hard to switch tools, apparently. Should be 3 in this region right here, accounting for the 6 not square reds. So how would I describe those 3 right there. This 3 I just wrote down more specifically. Let's see, they're red, right? And they're not square. And what else has to be true? Because they're not small. Yeah, so technically they're not small. We happen to have a name for not small usually. Big, large, well, what could be medium? Uh-oh. Do we have any medium shapes here to worry about? No, they're either small or large, so we're okay. But can you see that sometimes calling something large versus not small isn't necessarily the same thing if you have other categories? All right, let's take a look at the upper crescent. Notice I'm working from the inside out here. How would I describe things in that shape there? They are small, not squares. Okay, so let's see, small, not squares. These guys are all small, not squares. 3 times 4 is there's 12 of them altogether. I've accounted for 3 of them. So how many are in the leftover region there? 9. Yeah, there should be 9 in there. So we'll double check that in a minute. So we're guessing, clean that up a little. We're guessing that in this upper region, there must be 9 because we believe there are 12 things that are not square and small. So let's just double check that we got that subtraction right by describing those pieces right here. How would I describe something that goes in that like rocket ship shaped piece? Let's see, they got to be not square, right? They have to be small and they got to be not red. Okay, so let's double check. Let's see. Small, not squares. So I'm in the lower part, but not at the very bottom line. And they're not red. So I want those 3, those 3, and those 3. 3, 3, 3. That adds up to 9. Okay, I'm on the right track. Can you see how if we were dishing the pieces out on the table, this would be much easier? So we're having to twist our brains to really think hard and double check. All right, so let's clean that up and try. I think we're ready to do some more. What about, let's deal with the smalls for a minute. How many small shapes are there altogether? Yeah, there's 4 by 4 down here. And so in this red circle, there should be 16 things. Okay, we've accounted for 9, 10, 13 of them. So by deduction, I'm going to say, well, there must be 3 more I haven't accounted for. So let's see. How would I describe the pieces in this region out there? So if I just focus on this region right here, let's see. Those 3 pieces are small, right? But they're outside the not square region, so they must be squares, and they're outside the red region, so they must not be red. Okay, so I need to find pieces that are small, they're not squares. Well, they are, yeah, not squares. So they are squares, and they're not red. Okay, that's brain twisting. Small, okay, I'm down here. They're square, okay. They're in this group here, and they are not red. Oh, there they are. Those 3 here, this one, and that one. Small, not red, not square, which means they are square. Whew. That one's the tough part. I'm out, so let's use a different color here. Maybe that color right there. So anything in here has to be not a square, right? So if I'm outside of this region here, what must you be to be outside that circle? A square. So anything in here has to be square, small, and not red because it's outside of the red. That's getting messy. I need to clean that up. Let's see. Too many colors. I think there's 3 here, and I double checked they met the right requirement. All right, let's go. What has to live in this region right here? the inside that region, those are the not squares. Okay, so the not squares, I believe, are all of these guys right here. Okay, and let's see, how many of those are there? Well, there's 1, 2, 3, 4, 5, 6 by 4 is 24 of them. Okay, and I've accounted for 9, 10, 11, 12, 13, 14, 15 of the 24. How many am I missing? 9. Okay, so we think that there's 9 in there. Let's double check by describing those 9 pieces. So let's see. They are not squares, right? What else? They're outside the small area, so they are not small. So that means they must be large. So I have large, not squares. So let's narrow that down. These right here on my large, not squares. I don't want those guys. And they are also what? Not red. So I don't want those guys there. So it looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. I think we did it. We confirmed that by subtraction and by describing. So clean up our mess. 9 out here. All right. Ooh, blue circle. What goes in there? Reds. How many reds are there? Altogether, there should be 8 of them. We've accounted for 7 of them. So we think there's 1 right there. Can we confirm that? Let's see, what would that be? It's outside the not square, so it must be a square, and it's outside the small, so it must be large. So I believe we're looking for things that are large red squares. How many large red squares are there? There's only 1. Oh. Now, we've accounted for 7 of the 8 regions in this picture. What region have I not done yet? Outside all 3 circles. So now we have to figure out what should be outside all 3 circles. Okay, so let's see. If I'm outside the black circle, I must be a what? Square. Not a square, which is a square. Okay, so I got to be square. If I'm outside the red circle, I must be what? Not red, so I want square and not red. And if I'm outside the small, I must be not small, or in this case, we could say large. Okay, what shapes fit the square, not red, large? So large puts me in the top area, right? And then, so I can forget about these guys down here. Not red. So that means I either want this group, or that group. And then I got to be square. So that means I want this guy, or that guy. So there looks like there are 3 things that are square, large, and not red. The order I do those doesn't really matter, turns out. Okay, kind of like multiplying numbers. You can multiply in any order you want. You can add in any order you want. So I think there's 3 shapes that live outside of those 3 circles. So let's double check a few things. What do all of those numbers add up to? 9 plus 9 plus 3 plus 3 plus 3 plus 1 plus 1 plus 3. 32. So let's say I got 10, 10, that's 20, 9, and 3, 29 and 3 is 32. Yeah, it adds up to 32. Is that a good thing? Yeah, because in my grid of stuff here, I have 4 columns and 8 rows. 4 times 8 is 32. So either coincidentally, these add up to the right number, or I put all the numbers in the right spot. Let's test that out a little bit by asking some other questions. All right, so I'm going to erase this. Oops, sorry, I thought I turned that sound off. How do I turn it off? Like that. There we go. All right, so I want to erase it. So let's see. I would like to know how many pieces are not square and not red. See if you can figure that out by looking at the shapes or looking at the Venn diagram or both. So if you have the pieces in front of you, that can be very handy. Otherwise, we got to look at this setup here. So let's see, not squares are all of these guys right here, right? And I want them to be not red. So that would be this group, and this group there. So that gives me 6, 6, 6. I think there's 18 when I look at this shape right here. So now I'm going to go over to my Venn diagram. So I want to figure out, let's see, where does let's see, these are the squares, right? Except the catch is I have to be outside of the red region. I think what I want then is that region right there, right? I want the not squares, but I want to get out of the red region. So I could kind of say it's the not squares minus the reds. Take the reds out. And how many does my Venn diagram say I have? 18. Does that evidence that we made a pretty good Venn diagram? Yeah, we did pretty good. Okay, I'm going to stop this recording here. I might start a new one in a few minutes. So stop.